This lecture is on a topic that's a bit different from the other lectures. This one talks about a particular application that's very important these days in computer science, which is to trying to figure out how to place ads. Basically, the internet, the way most websites get paid is by ads, and so one of the biggest problems is how do we choose the right ad to place at a particular time in order to maximize our revenue. And this evolved out of, I had an internship with Yahoo some years ago, and Yahoo these days is basically, their main thing that they work on is trying to place ads. Search, I think they no longer do, that's being done by Microsoft, and their news is not a primary thing that they work on. Really, ad placement is the thing that they're most interested in. So here I'll talk about some models for trying to think about how we can place ads. They're not going to be very realistic, but the idea is just to get some idea of what we can do, at least with simple situations. And in particular, these will be applications of two larger classes of models, which are the stochastic knapsack and the multi-bandit problems. So the main problem, again, is some user appears on a website. We have a bunch of different ads. We may know a lot or very little about these ads. And we want to figure out, well, which ad should we display? So again, I'll first talk, and as I mentioned, I'll talk about kind of two models being applied to this question. The first is a stochastic knapsack, and the second one is multi-arm bandit problems. So part one, stochastic knapsack. And here, so first let me say something, just how usually ads work, right, is so some company goes to, say, Yahoo or some other company that does ads and says, well, we have some ad, and what we want is, so some companies will say, just display this ad, and we'll pay you just for displaying it. This is especially good for very big companies that don't necessarily want you to do something now, but just to remember about them. So, you know, so some large company like Toyota or well, any really large company, Sony, Samsung, they might just want to have their name there just so you remember about them, and they don't care if you click or not. But for a lot of other situations, the company really cares whether you click on the ad or not, and you only get paid if there's actually a click. More generally, you can be paid, so what they say is not so much for a click, but for a conversion, which could be a click or something else. So there are situations where you only get paid if somebody actually purchases something. They click on the ad and they buy something. Or they click on the ad and they do something. Maybe they have some game or something they want people to play as kind of additional advertisement, and if the person doesn't do that, you don't get paid. So really what we care about is conversion, and usually you get paid just per conversion. But let's consider a situation where you get paid not per one conversion, but you need to guarantee a certain number of conversions before you get paid. So let's assume that for some ad you have to guarantee, say, n conversions. Otherwise, if you only get a couple, you don't get paid. And the motivation for this kind of a model comes from websites such as Groupon. So Groupon is a website, I assume you probably are familiar with it. And, I don't know if they're in Russia or not, but basically Groupon is a website which offers various kind of deals. So for different services, different restaurants, they'll say, if you, we'll give you a deal that you can get a very nice discount. But it will only work if a certain number of people actually sign up. So if less than this number of people sign up, then nobody gets it. And the idea is that you're supposed to, at least the motivation for these kind of ads is you're supposed to go out and kind of tell your friends, oh, there's this really nice deal on Groupon, so why don't you go and buy it too? And at least that was the original idea, and so that way you would wind up getting enough people that the deal will be on. But the idea is if not enough people sign up, then the restaurant doesn't really have enough motivation to offer such a nice discount because they're not guaranteed essentially a certain number of people that will come and take advantage of it. And in that case, the deal is off and nobody gets this. So we could think of these kind of ads where we need to guarantee a certain amount of conversions basically being a situation where we need to get enough conversions for the deal to be on. So the conversion will be just that somebody goes to the website and actually purchases this, and enough people do that, so the deal is on. So if the deal is not on, then we get paid nothing. For us to get paid, we need the deal to be on. And I should mention there's plenty of other websites that do it with this similar approach. Okay, so let's construct a mathematical model of this situation. Admittedly, simplified from what really happens, but we call this the chunked reward model because the rewards come in chunks. Instead of just per each conversion, you have to get a certain number of conversions before you get anything.
May I ask?
Yes.
So there is one thing that appeared to me for a couple of years. I don't know how to call it in English, so контекстная реклама, some context ads, or and it is widely used in Europe also by Amazon and websites like this. That if somebody is looking for, I don't know, for a car on some website, that when this guy will enter other websites, he will get, by Google for instance, he will get some advertisements related to cars. So in some sense, your connection with internet is not secure, and so internet in some sense knows what I'm looking for, and if you enter other websites, you will get these special ads on the topics that you're interested in. So do you consider also these things?
So we don't consider this. This is actually one of the things I'll talk about later as kind of extensions or open problems, which I think this needs to be extended to. Because in general we do have a lot of context, if not just, first we know a lot about the person through cookies, and also different websites will definitely have different probabilities of clicking on various ads. So that's certainly an important question. We didn't address it in this work, but certainly that's something that is important. And that's, as I mentioned, we're definitely going to make several major simplifying assumptions, but in principle, that's certainly something we would need to consider. Okay, so the mathematical model that we will consider is as follows. So we assume that there are k ads, and we have until some time capital T, or I guess fancy T, and for each ad we need a certain number of conversions. So for the ith ad we need to get n sub I conversions before time fancy T, and if we do, we get a reward r sub I. Once we get the reward, we assume that no more money can come from this ad, because we can think about, okay, the deal is on, they don't necessarily need any more people to do this, so we don't get a reward once we have done n sub I conversions. Okay, so further assumptions, we assume that users are IID, and this is exactly what you were kind of criticizing. They're not in fact IID because we have a lot of information about users, or at least about the websites. So this is definitely a very strong simplifying assumption, but we make this assumption within this model. So specifically, we assume that when a user is shown an ad, she will convert with probability p sub I, and that this is true for all users. Again, this is a simplifying assumption. And in particular, this means that there is no ad fatigue. In practice, people, after they see an ad many times, they didn't click on it the first time, they probably won't click on it again.
So we could have a profile, statistics of the type of users, yes?
Yes.
So it makes sense to consider model where you have some distribution, prior distribution, what are typical proportions of preferences for different users.
Yeah, exactly. So as I said, this is very much simplifying assumptions, but this allows us to get some reasonable results. But of course, in practice, we have quite a bit more additional information, and the users will not be IID, but with with what we know about their previous search history, or even just what website they're on, that will affect their probability of clicking on an ad.
One question about the previous slide. So
yes.
The ads are equivalent, or consider?
No, so the ads, they have different probabilities of a click, they have different rewards, and they have different amounts of conversions that they require.
No, I mean these ads are about the same topic, or it doesn't matter?
Not necessarily. In this case, it doesn't matter because of, again, with a simplifying assumption, of course. If we looked at everything we know about the user, then that would affect the probabilities based on what this object, what kind of ad this is. But in this simplified model, it doesn't matter what kind of ads these are. Is that correct?
Yes.
Okay. Yeah. So we assume that we know the probabilities. So of course we have some time, fancy T, but until this must happen. But the number of actual users that will come to the website before that time is some random variable. So the number of actual opportunities we have to display the ad is a random variable, capital T, which has some distribution f sub t. And again, we make some strong assumptions that we know or already have very good estimates for the probabilities of any ad being, or for us to get a conversion for any of these ads, and for the distribution of t, how many users we expect to visit these websites up to time fancy t. So that's the basic model. And in this setting, we want to optimize our reward. And this is a version of the stochastic knapsack problem, which is itself an extension of the deterministic knapsack problem. And I don't know if everyone is that familiar with these problems, so I'd like to talk a little bit about these basic problems, and then how we can extend on the ideas of solving these problems to the case where we're actually looking at. So probably right now me saying it's a stochastic knapsack problem doesn't necessarily mean much to those of you who are not familiar with the stochastic knapsack, but maybe, so that's why I think it's good for me to just a little bit describe knapsack problems, and then we'll be able to understand why this is the framework we're actually working in. So before proceeding, let me just give some background. And the way I like to think of the knapsack problem is basically you're a thief and you sneak into a store and you have a knapsack where you can place various objects from the store. But your knapsack can only hold a certain amount of weight, capital T kilograms. Now, this is deterministic, so everything is deterministic. Capital T is deterministic, and everything we know about the objects is deterministic. So the objects that we have, they all have some weight, and they have some reward, how much they cost. So ideally, we want to put as much into the knapsack as possible in terms of reward. So we want to maximize our reward, but we have this constraint. We can only carry up to capital T kilograms. So to write this very formally, we have k objects. Each object has weight wi and reward r sub I. And again, we want to maximize our total reward without exceeding the weight capital T. It's well known that this problem is NP hard, so trying to look for an exact solution, well, it doesn't make much sense. But what we want is a good approximation algorithm for how to try to solve this problem. And later, this kind of this exact approach we will extend to the problem that we're discussing. So let's consider relaxation, which is this is called the fractional knapsack problem, where instead of just having whole objects, we can take any fraction of an object. And so if we take for the ith object, if we only take gamma sub I of it, which is some number between 0 and 1, that's kind of the fraction of it we take, then the weight of that will be gamma sub I times the weight of the ith object. And the reward will be gamma sub I times the reward of the ith object. Задача в рюкзаке.
In this form, it's not as we had already.
Yes, in this form.
It's quite simpler.
Yes, next slide, or maybe in 2 slides, I will give the the optimal solution in this case. So this is a relaxation, in which situation we actually have an optimal solution. And well, in this case, we could think of it where these are objects that don't have a very strict size, and we could just take parts of it, like, for instance, with coffee. Okay, so this problem is very old, and back in 1957, Danzig already solved this and proved that the optimal solution to the fractional knapsack problem is just to insert the items in order. So we basically just look at the relative reward relative to how much the object weighs. We ordered these, right? I've reordered them, so R1 is just so 1 is just the object which has the largest R1 over W1, which means kind of the reward per unit weight is the best. And intuitively, this should be the solution. And Danzig proved that, in fact, this is the optimal solution in the fractional case. So what we could do is we could say, well, if this works well for the fractional knapsack problem, we could try it for the regular knapsack problem, and hopefully get something reasonable. So let's call
Excuse me to interrupt you. The previous slide, so
yes.
actually the solution is you take as many, starting from the biggest one, you put as many as you can, and the last one you cannot put wholly, you just put the fraction.
Exactly, yes.
Okay.
And then, of course, for some of the last ones, like RK or like the kth one, maybe we can't fit any of it at all.
Okay.
I assume that if the knapsack is large enough, that will be nearly optimal even for integer problem. Not exactly optimal, but roughly it's nearly optimal. So it's not a big fuss about the P problem and all this stuff. It's nearly the same.
Yes, so yes, absolutely. Really, I think that at some level this solution gets kind of to the truth underlying this situation, but the very specific numbers that we have and having to stick with them is really what causes problems with this for the non-fractional case.
Okay, but asymptotically, forget about all the things, problem, and just do it like this. And I don't know what would be the error, but it would be clearly very small.
Yeah, definitely. I think that this solution really gets to kind of the underlying truth of the situation, and really the only problem that can happen is if we have one object that's very large, and also has a large reward. And that's basically what the problem with this situation is.
The problem is if this large object, unique object, taking a single part of the whole package. If it's asymptotically negligible, again, we come to the same. If it's with a bigger part of the whole volume, then you have indeed these problems with NP and all this stuff.
Yes. If the size tends to infinity.
I mean, the fraction of this particular one single item is asymptotically prevailing somehow.
Asymptotically, which size?
You take bigger knapsack.
Yeah, you take bigger knapsack. You maybe take more objects, but the object sizes don't grow too fast. Then I agree.
Then it should be still the same stuff.
Yeah.
Yes.
Yes.
I have another question. So I understand that this is an optimal solution, but is it true that you can do? I mean, is it a unique one in the sense that I understand this is going to be the optimal solution with the less object possible because you're taking from the bigger one to the smaller one?
Mm-hmm.
But is this true that any solution? I mean, if you start by R2 to R3 and you go to smaller objects, I mean smaller coefficient objects, then if you put them as much as you can and then you take the fraction of the last one you cannot put, is it also going to be optimal? I mean, you can I mean, if you have a lot of objects, and can you start from R3 and going down, R4 going down? Is it true?
True.
Okay, so it's not up to, it's not unique.
No, I think
Because,
that
I mean, you could start by RK, taking objects bigger and bigger with bigger and bigger.
Yeah. I think that there's so you could I'm sure you could construct examples where you would have other optimal solutions, but in general, I don't think that.
Because if you authorize fractions, I mean, it looks like you have as many solutions as you can take permutation.
But you-
Not permutation, but
No. This solution is unique if there's no restrictions. You can take any objects. That's unique, I believe. If to say, okay, some item are excluded, then you will have more substitution. Okay.
Yeah, I'm not sure. I'm pretty confident that this. You can definitely find situations where there is no other solution.
I mean, in general.
Yeah, in general, I think this will be the only one. You might be able to construct specific cases where, because what you're doing, if you're excluding, say, R1, you might be R1 over W1, you might be excluding the case where you have the most reward, and the rest might have very small rewards. So skipping or missing some of these, I think, some of the larger ones, I don't think you can make up for it by the later ones, because
there are equalities, of course.
Oh, yes, of course. Yeah. So no, I think that this would, at least in general, you might be able to find counterexamples, but some special cases. But I think that you can, in general, this should be unique. Okay. So what happens when we apply this to just the regular non-fractional knapsack? Again, I completely agree that in some asymptotic sense, this is kind of the right thing, and there's a lot of kind of truth to this idea. But let's say policy pi1 is that we apply this to the regular knapsack, and we just put in the objects that we can fit the whole piece. But then the last object, if we can't fit all of it, then we put none of it in, because we're not. Because we are in the non-fractional setting. So the last object we might need to not include at all. Now, this is a very good policy, and in many situations it will work very, very well. But you can construct examples where it's arbitrarily bad. And the problem with it is that we might have one object that's just has a large reward and a large size. But we can do kind of an analysis on this. So let's consider the optimal reward we can get just in the integer, the regular knapsack problem, clearly is upper bounded by the optimal reward in the fractional setting, because that includes the integer setting as well, right? So so there's more things we can do. So it's upper bounded by the optimal reward in the fractional setting. And this is upper bounded by, right, for the first, up until the last object, the rewards are basically the same. That's the reward from pi1. So the only issue is this last object that we might not fit completely in. And we fit part of it, so we get part of that reward. So certainly the full reward is going to be the following. So for the full reward for the optimal policy is the reward from pi1 plus whatever fraction of the last object we get, whatever reward from that fraction, which is of course upper bounded by the reward, not the fractional, but the whole reward, and that itself is upper bounded just by the maximum possible object that we can get with a reward.
Reward is the sum of Ri?
I'm sorry.
Reward means
reward is how much
much amount of Ri.
Yes, the total Ri that we have in our knapsack at the end.
I
Yes.
don't understand the first inequality. I'm sorry.
Oh,
Is it obvious?
Optimal reward to optimal reward in the fractional setting.
Yes.
So think of it in the fraction. Any policy we have in the integer setting, we can also use in the fractional setting. So and we'll get as much reward in the fractional setting as we would.
Usually reward is partial
Yeah,
case of
okay,
fraction.
first.
It's clear. The last one, because The remaining part may be any of this.
Okay.
You can take maximum.
Yes, exactly. Yeah. So and then we have what we got from the that we fit in all together. Plus we might be missing a little piece, and that piece is clearly upper bounded by the largest possible reward of anything. And well, so clearly this sum is upper bounded by 2 times this maximum. So this kind of leads us to a new policy which says we follow pi1 if the reward from pi1 is larger than the maximum reward out of anything that we have. Otherwise, we take the item with the largest reward. And it's clear that the reward of this is exactly going to be the maximum of these of the rewards from these 2 policies. So it's exactly this term. And so we can divide now both sides by 2. And we see that from the reward from pi2 is bounded by, from below, by the optimal reward divided by 2. So if we follow this procedure, we're guaranteed that we will never do worse than 1/2 the optimal reward. And it can be shown that the bound is attained, so at least...
It's right.
I'm sorry?
No, sorry.
Oh, I think what you're getting at is kind of my next point. It's clear, of course, we can improve this algorithm because once we do pi1 or whichever, once we do pi2, we might still have room left over, and we might be able to put additional items into it. So we can actually improve this reward. I think what you were suggesting, we just with whatever's left, we just do the same procedure again.
The lower bound goes to the optimal one.
Yeah. So then we'll definitely do. So in that sense, we can do better than just this reward, than just this policy by making sure we, if possible, we fill in the rest of the knapsack.
I'm pretty sure if the goods have random parameters, that's much better than a half. It will be very close. It should not be half of but some number which is much better. Say, take a probability for distribution, all this, take all the statistics. I don't know exact numbers, but maybe you know the answer.
I will get to at least one situation where the rewards are random,
Yes.
with an exponential distribution. There, it's actually.
It should be very close.
There, it's actually it is optimal in that case. And although I won't discuss it here, in the case when you still have fractional problem, but if the knapsack size is uniformly distributed on some interval, it's going to be optimal as well. So definitely, when you add a bit of randomness, at least in certain ways, you can get that this is optimal. Okay. So there's many different ways that people have extended the knapsack problem into a stochastic problem, but the one that's most relevant for this problem of ads that we'll later formulate as a knapsack problem comes from 2 papers by Dean et al. And here the idea is that we allow the sizes of the objects to be random. We know there are distributions, but now they're random, and we want to maximize our expected reward in this case. So they consider the case where the knapsack size is fixed, but where the objects are random with known distributions. So to put this very formally, now again, assume we have k items as before. Item I has reward r sub I and weight w sub I as before, but now every single one of these w sub i's has some distribution f sub I. Yes?
I just want to know your opinion. Could you cope with the problem when you see object one after another? So first you see object, you decide take it or not to take. Then you see second object. Is it standard?
Yes, that's
common. Okay, so you just learn one object. And you take decision, take it or not to take. Then you move to second object, etc., etc. So What would be done in this situation?
So I haven't studied it, but I've seen there's many papers on this. It's called, I believe, the Stochastic and Dynamic Knapsack. It's kind of a version of the secretary problem
Yes,
combined with the knapsack
absolutely.
problem. So it's definitely been studied, but I couldn't tell you the details. Okay. Yeah. So here the model we're looking at, again, we have k items. Each one has some reward, let's assume it's fixed, and some size, which is random from a known distribution. So Wi has known distribution f sub I. Right, so we assume that f sub i's are known and that the Wi's are all independent of each other. And the way we do this is, so we know how many Wi's we have, we know their distributions, but what we do is we put them into the knapsack, and then we see how big they are. If they're too big, that means we get, if the first one we put in is too big, then we get no reward whatsoever. Otherwise, whatever we get the reward if it fits in the knapsack up until it doesn't fit. And so we still want to maximize, but now instead of being able to maximize our reward, we want to maximize the expected reward. And let's still assume that the knapsack size t is non-random. We'll later remove that assumption, but for now let's assume it's non-random. And maybe it's better to think of this as a scheduling problem. In this case, right, we have k projects, and we need to pick one of the projects, we run it, and all of them need to be done before a particular time, but the amount of time they take is random. So first we do one project. When it's done, we then pick another project, and so forth. So up to some fixed time t. And at the end of each project, we get some reward. And of course, if we don't finish a project, we don't get a reward from it.
Why are you considering random weights but not considering random rewards?
So I will talk a little bit about random rewards at the end of this discussion. But basically, because in the ads application that I'm interested in, we basically can assume that we know what the rewards are. I guess you could talk a little bit about credit risk, and I will briefly discuss that extension at the end.
Could was a question that if you have some restrictions, that you cannot start some other project before you finish the previous project, and still the same problem. It would be a very hot topic called tropical mathematics. It would be some hot topic for algebraic geometry. Tropical mathematics.
Why tropical?
Because it was invented in Sao Paulo
Ah.
by one of my colleagues.
Well, that's interesting, but yeah. But here we're assuming that there is no such relationship. But certainly that's an interesting additional constraint on this that could be considered. So this is maybe a slightly more realistic way of thinking about this kind of stochastic knapsack problem. And so again, this problem goes roughly was formulated in this way in a paper by Dina, in two papers by Dina et al. And they propose various approximations to this, including one which is a 4 approximation. So they guarantee that it's within a fourth of the optimal solution. And interestingly, it turns out that there's situations where actually you get the optimal solution. And although the problem, as stated, was formulated in Dina et al. In a slightly different formulation, thinking more in terms of a scheduling problem, this had been solved back in the 70s by Derman et al. And I'd like to discuss how they solve this problem in that case. So assume that the Wi's are all exponential random variables, but with potentially different means. So in this case, the optimal policy to take turns out to be, well, basically exactly the optimal policy from the fractional knapsack. We take Ri, before it was Ri divided by Wi, well, here it's Ri divided by expected value of Wi.
Just very difficult to know your opinion. If both are random, what we should take expectation of ratio or ratio of expectation or something else?
If they're independent.
Both independent.
So Ri's and Wi's are both random. At least in the way that I was approaching it, I think you take expectation of Ri divided by expectation of Wi.
Yeah, there's no ratio.
Yeah.
Yes. It's still perhaps the answer would be the same. Yeah.
Yes,
Yeah.
yes, the answer would be the same because we're under the assumption of independence.
Yes, that's
I guess that in this case, through conditioning, it's quite straightforward. This result.
yeah. Also, that's his feeling.
Yeah, it's not very complicated, but I did want to go through the arguments, and the argument basically is based on this fact, which is true for exponential distributions. It's a very simple. So tau, I'm assuming, could be a random variable, but it's always greater than or equal to 0. And independent of wi. So by a conditioning argument, it's enough to show that this result is true when tau is just a fixed constant. And to show that, it's basically just a straightforward calculus problem. Just evaluate the integrals on both sides and see that they're equal to each other. So I'm not going to verify this because it's just a straightforward calculus problem. Okay, so we think about this now, so let pi be any policy for doing this. And let ti pi be the random time when policy pi begins inserting item I. If pi never inserts item I, then let's just take ti pi to be capital T, so at the very, sort of just, it's never going to get there if it starts at the time capital T. And note that the ti pi is independent of wi. It might depend on all of the past, all of the w's from before, but all of those were independent of this one, so we still have that ti pi is independent of wi. And now we can say, well, the expected total reward under pi is just going to be the sum of the rewards times the probability that the sum of the over Ri times the probability that we actually managed to fit Wi into our knapsack. And using that equality at the top, we can rewrite it in this way. Now, what's interesting is this is also the reward from a certain fractional problem. So consider a new problem. We still have a stochastic knapsack, same items, but now the ith item has reward Ri lambda I Wi. And it weight same weight Wi. Then in this setting for the fractional problem, this is exactly the reward for the fractional problem, the expected reward, because we have Ri, right? Lambda I times the expected value kind of the part of Wi we managed to fit in. So this is exactly the reward from the fractional problem. So it means that there is no difference in this case between the fractional and the the slightly modified fractional problem and the original non-fractional problem. So we know what the optimal policy is. We need to take Ri lambda I Wi divided by Wi, which is exactly the ordered by Ri lambda I, which is what we saw, which is what I earlier claimed was the optimal solution. Now the optimal policy doesn't depend on t, and so it will remain optimal even if t is random, so long as it's independent of everything else. By a very similar argument, we can get a similar result for the geometric distribution. Right? I mean, geometric is kind of like a discrete exponential in some sense. And so we can, if the weights are geometric, then we can use the same policy and the proof is basically the same. And so in that case, we need to just order the items by Ri times Pi. And this will be optimal. And again, it will remain optimal if t is random. And even if we're allowed kind of at every discrete time point to switch the policy because it doesn't depend on on time, it will still remain optimal in that situation. Okay, so that's a little bit of background about the knapsack and the stochastic knapsack problems, and kind of the known results, at least the ones that I was aware of when I started working on this problem. So let's just remember what the problem is. We have k adds. The ith add has reward r sub I and requires that we get n sub I successes. So let wi be the number of times we must show this add in order to actually get these n sub I successes. But if we think about it, right, if n sub I is just 1, this is going to be a geometric, right? We just need, it's just how many times we need to show it before we get our first success. If n is greater than or equal to 1, it's going to be, in general, some negative binomial distribution, right, where we need, right, number of times we need to show the add before we get n sub I successes. So basically we need, we in the case for geometric, it's solved, but now when we have this additional issue of chunk rewards where we really need to show n sub I, we need to really get n sub I conversions, it's going to be negative binomial. So how can we maximize the expected reward in this case? So yeah, negative binomial, of course there's multiple parameterizations, but this is the one that we need here. Okay, so so this is a negative binomial situation, and it's not difficult to see that if t, the number of times we're allowed to show this add, which is in general random because it's the number of users we have until time fancy t, if it has the bounded support, we can easily construct an optimal solution. Not easy to implement it, but easy to come up with a, it'll be very, they take a very long time to do it, but we can get an optimal solution in this case.
Philosophically, my instinct is to optimize mutual information between your stream of ads and stream of clicks somehow. This should be not difficult mathematically, not very difficult, but I would optimize the weight somehow, but mutual information. You have, okay, we can discuss about the principle, maybe you thought in this direction also.
I have not thought in that direction. That could be,
would be a very natural thing to do.
That could be quite interesting. That's not,
Okay.
yeah, I kind of thought more along the lines of the approaches that I discussed with other kind of knapsack problems, but it could be a very interesting approach as well. Okay. And of course, again, since the regular knapsack case problem is a special case, in general, the optimal algorithm will be intractable, even though it exists. But we proposed kind of, maybe a little bit intuitively, two greedy policies. I think we actually proposed more in the paper, but here I'll talk about these two greedy policies, which is, so gamma 1 is exactly this kind of a fractional idea, Ri divided by expected value of Wi, which turns out to be Ri/Pi over n sub I. And of course, we only need to consider situations where, things would actually fit into our knapsack. If with probability 1 it won't fit, then there's no point considering it. And we also tried also weighting this by the probability that Wi is less or equal to t as well. I'm not sure it really helped much, but we considered these two policies. And again, I think there's definitely, as with using the fractional knapsack problem to try to deal with the regular integer knapsack problem, I think there's definitely some truth to these indices and to following these policies. But again, because of certain kind of strange situations, we can find examples where they're arbitrarily bad. And the problem is similar with the problem with using the fractional for the integer one. There might be situations where we just have very relatively small probabilities, but really large rewards. And and this policy both of these policies kind of discount those too much, and we miss the possibility of getting these situations. I kind of think of it in terms of, if you know the card game Hearts, you have kind of two situations. Either you never take hearts or you always take hearts, but if you always take hearts, you need to make sure you get all of them. So that's kind of what happens here. Usually you don't want to take take the risk, but sometimes it's really worthwhile to take the risk, and that's the situation that can cause problems with these policies. So instead, let's consider a policy, gamma 0, not maybe a very, let's just consider gamma 0, where we choose an ad which maximizes the reward times the probability that it fits. In other words, it maximizes the expected reward, expected in terms of what we could either get it or not get it, so maximizes over that expectation. Right, so this is the kind of equivalent of taking the item with the largest reward in the integer case. And we'll keep using the same ad even after we've received the reward for this ad. Not a very good policy, clearly one that can be improved, because in the same way that the regular knapsack problem could be improved, as we discussed, you could always add more stuff at the end. We could always improve this at the end, but just for simplicity, in order to get some theoretical results, let's consider the case where we always choose the same ad even after it's totally useless for us. So that's gamma 0. And now let's consider modified policies. So we have our policies gamma 1 and gamma 2 from before, which seem to get at what we want in this problem. But we know that there's some situations where they're not as good as kind of gamma 0. So we could say, well, if the expected reward from gamma 1 is larger than that from gamma 0, we go with policy gamma 1. Otherwise, we go with policy gamma 0. And we could do a similar comparison with gamma 2. Or we could say, well, we randomly choose between these policies. With probability half, we choose gamma 0. Otherwise, we choose gamma 1. Or with probability half, we choose gamma 0. Otherwise, we choose gamma 2. So we have two different ways of choosing between our two policies and gamma 0. Of course, intuitively, the second way of doing it is much nicer. We can evaluate the expectation, especially if t is non-random. But if t is random, finding this probability may not be that straightforward. We can use some Monte Carlo methods to do this. But basically, the problem could be in evaluating the expectations, which is why we have policies gamma 3 and gamma 4, which clearly aren't anywhere near as good as gamma 5 and gamma 6, but they're ones that we can implement without having to worry about how we evaluate these kind of expectations. Okay, and so the theorem that we can show is that, so we have the optimal policy is bounded by, well, we get these kind of bounds. It's how far, how we can relate it to these expectations.
We understand that this smaller than minimum of your four expressions, all these different expressions on the right side, or just minimum of four formulas. What do you want to say?
No, so what I'm saying is that, so here of course...
Minimum.
On the left-hand side, it's always the same term.
So left-hand side is smaller than minimum of four expressions. That's what you want to say, yes?
Yes, that's the equivalent, that's the equivalent way to think about it, yes. And this basically tells us how we can relate our policies to the optimal policy. And if we kind of bring these over, one over these on the other side, we know that we can't be too much worse than the optimal policy. We have some lower bound. It's written as an upper bound, but really this gives us a lower bound on the expected reward of our policies in terms of the optimal policy. So in particular, we could say probably won't choose policies or ads where the probability that we'll fit the ad, even if it's the only ad we fit, is very small. So if we restrict ourselves to the case where the probability of being able to fit any ad into our knapsack, if it's the only thing we ever show, is greater than 0.5, then we can show that gamma 5 is within within this kind of restricted class of weights. We can show that the optimal policy is within 1/3. I'm sorry, that policy gamma 5 is within 1/3 of the optimal policy. And for the rest of the policies, they're lower bounded by 1/4 times the reward from the optimal policy. So that's one way we could think of the formulas here, to simplify them. Okay, so how can we prove the theorem? The idea is, so let's consider a fractional problem where of sorts, where instead of add I requiring n sub I adds, we with reward Ri, we assume that we decompose every single one of these adds and just say, well, let's assume that we get reward Ri divided by Ni for every single click, right? So every time we get a conversion, then we wind up with a reward Ri over Ni. And so now our adds are, we can index them I comma j, right? I for each one of our original adds, and then the j's go from 1 to n sub I, which is kind of the geometric distribution for each one of our clicks. So we're assuming that every single time we get a click, we get reward Ri over Ni. Now, in this case, we're in the geometric situation, which we just discussed a few slides ago, and we know that the optimal policy is to follow this kind of greedy index Ri pi over Ni, which is basically our policy gamma 1. So in this fractional problem, we have an optimal solution. And now we can proceed basically the same way as we went from the fractional to the integer in the deterministic case. So for any policy pi, the optimal policy is, the expected reward from the optimal policy is clearly bounded from by the expected reward in the optimal policy for the fractional problem. And that, again, is bounded by using the fractional problem to in the non-fractional case, except, of course, the last one, if we don't get all of it, we get nothing. Plus the maximum reward, and it's really just maximum reward because we have P of Wi less or equal to T divided by P of Wi less or equal to T, so that's just 1. I just introduced that for convenience. But basically this formula is up to expectation, exactly the formula we had in going from the fractional to the integer case. In the deterministic situation. And now we can clearly upper bound it right by in this way. And this turns out to be exactly the expected reward from policy gamma 5. So the approach is very similar, basically the same approach as we had in the deterministic case, but now kind of with expectations. And similarly, in the case where we have, where we randomly choose between gamma 1 and gamma 0, we can kind of write, we can upper bound that in this way here, right? We have 1/2, 1/2 being canceled out by this 2. And then this is exactly the expected reward in the case where we randomly choose between the two policies with equal probability. And so that's how we get the bound in this case. So that's basically where or how we can prove the theorem. Again, in the sense, again, basic approach is just the same as the deterministic case, but with expectations. Okay, so now I want to say a little bit about extending this to the case of random rewards. So since we're interested in maximizing the expected reward, really nothing in this would need to be changed if the rewards are random, except that we just take the expected value. And everywhere I have Ri, it will just be expected value of Ri. And as I think I mentioned briefly at the beginning, in terms of ads, the interpretation could be that there might be some credit risk. Some company asks you to show some ads, but then they might go bankrupt before they're able to pay you.
Maybe fraud as well.
Could be fraud as well, yes. So, so that's kind of how we can interpret this situation. So let me briefly mention that there's many extensions of this problem that I think are worthwhile considering. One is, of course, there might be a penalty for not completing the contract. We kind of promise we'll get a certain number of conversions. Okay, fine, you don't have to pay us for it, but maybe it makes sense that we would have to pay some penalty, and then that would create additional questions about how we choose which ads we commit to. And then this issue which was raised at the beginning of the talk, well, really we usually have a lot of context. We know we have some cookies from the user, so we know something about what the user is interested in. We have, we know what website the user is currently on. So that gives us some additional information that we would like to incorporate, and this would change what the probabilities are. So what the effect of that would be, I think.
They put some advertising and they slide some accumulators accompanied CPS for the screen. Okay. This happens quite often in real life. Okay. They put some advertising, say, pay some little money towards, as soon as we accumulate some sum, we will send you some rewards, etc. And as soon as part accumulated, they disappear. So it's also kind of inverse, inverse problem.
Mm-hmm.
So we have positive kind of goods and negative kind of goods simultaneously.
Yeah, so yeah, that could be. And let's see. So of course, another situation is that realistically, right? We display an ad, but it's not like if the person's going to click on the ad, they're not going to do it immediately. And there's probably somebody else coming to a website, that we are working with before we know whether the person clicked on the ad or not. So what do we do in that case? Because in reality, there's a lag time there. So that's a further extension. And the last extension that I mentioned is kind of an open problem is, well, in practice, we probably don't know what the probabilities actually are and how we can try to estimate the probabilities. So in the context of this chunk reward model, I don't think anyone has considered that, but that is, of course, a very, very important problem for ad placement. What is, how do we actually figure out what the probabilities are at the same time as we're trying to maximize our reward? And so if we kind of leave this model of where we have to get more than one click and just think, well, of the more standard one where we just need to try and maximize how many clicks or conversions we get, that problem has been very well studied, and that's the multi-armed bandit problem. Or it can be that problem can be formulated as a multi-armed bandit problem. So let me give some background on multi-armed bandit problem. So a multi-armed bandit problem is basically a machine with k arms. A one-armed bandit is a slot machine. So a k-armed bandit is when we have k slot machines. Each might have a different probability of us winning. And basically what we want to do is figure out, well, which slot machine is the one that has the highest probability of us winning. We can assume maybe they give us the same amount if we win, but they have different probabilities. So how do we, at the same time, we want to learn this and not lose too much money playing the wrong slot machine. So that's the basic idea of the multi-arm bandit problem. So, so again, we have...
There was some guy in Oxford, Jones, maybe I'm wrong with his name, who introduced some indices, which is this problem. We don't know, maybe Jones, I don't know, I remember him, but some indices like this ratio and update them, and he has a book.
So I know the most famous such index is Gittins index.
Gittins, yes, John Gittins, I think. Yes, John Gittins, yeah. That's what you're talking about, yeah? John Gittins, kind of...
yes, I won't specifically talk about Gittins results,
yeah.
but it's that kind of a framework. Okay, all right, so we have a machine with k arms. The ith arm gives us some random reward coming from some distribution f sub I. The reward may be positive or negative, although in the situations we'll consider it be basically 0 or 1, click or no click. The distributions are unknown, but we assume that they do not change over time. That is maybe a simplifying assumption. In reality, for ads, they can change over time, right? You've seen an ad a couple of times, and now you've either clicked or not clicked on it, so the probability of a click goes down after a while. But again, as a simplifying assumption, we assume that the probabilities do not change. And we assume that each of these distributions has a finite mean, and that the rewards are independent both in time and across all of the machines. So now, how do we maximize our reward in this setting? So again, I'll give two examples, but the one example that I'm mostly focusing on is this one with internet ads. But let's say we have k ads and we don't know the probability of a conversion. So which ad should we display in order to maximize our revenue, right? So we have simultaneously, we need to learn the probabilities and make use of what we learn and try to maximize our reward. Another maybe more classical application that predates internet ads by quite a bit is that of medical treatments, where we have k treatments and we need to figure out, well, which is the best treatment, but at the same time, right, a patient comes, we want to give them the best treatment, and yet we also want to figure out...
Giddens, he told me that the most important applications are clinical trials. When you have a new drug, and you should decide whether you have enough information to approve it or disapprove. So if you have somehow, should we continue more trials with this drug, or it's good enough for approval? So he wrote the whole book on this topic, and he said this is the most important application of clinical trials. And he wrote a lot about this. Okay.
Okay. Yeah, this is definitely a very important application. And again, this is kind of a situation where we simultaneously need to learn about how good different treatments are and also use the best treatment. There's additional issues with applying this to medical treatments, because with medical treatments, there's additional ethical questions that you don't have with ads. But mathematically, we could formulate in a very similar way. Okay, so let me discuss some policies that are used for in the context of internet ads. And one is the situation, let's assume that we know exactly how many times we'll be displaying the ad. So somebody pays us and we know we'll display the ad 1,000 times and that's it. If we know that, then what makes the most sense is let's do all of our exploration at the beginning, and then we just make use of what we've learned. So let's fix some epsilon greater than 0, And the first epsilon times t tries, we just randomly choose which arm we want to pull. So we randomly choose which ad we display.
It's like you have a hospital, you have some number of patients, and you treat them. You want to use the drug you believe is the best at the moment, but also you want to try other drugs. When the better, a little bit better also. So you completely decided which drug to use for this particular patient. This kind of thing.
Yeah, so that's the kind of clinical trials application. And again, that of course has very strong ethical issues, and you also need to have a lot of information ahead of time before you even get to the point where you can give the drugs to people. In the case of ads, you get a bunch of ads and you know nothing about them, but it's okay. You're not going to harm anyone by showing an ad that they don't like. So we don't worry too much, but let's say we get these K ads. We know absolutely nothing about these ads to begin with. So we start and we say, okay, the first epsilon times t tries, we just randomly show the ads. This way we learn something about the ads, and then at the end of the epsilon times t try, we just say, okay, let's just always show the ad which thus far has gotten the most clicks. Right? So I star is well, in general, if it's not the distribution, the rewards don't have to be just 0, 1. So in general, it's the total reward we receive from arm I divided by number of times we tried arm I, or in the case of
say formally, what will be the analog of this index in your context? How you define this index in your particular context?
So, well, I guess I'm not, I mean, it's not the Giddens index, but the index we use is right after so if you know exactly how many times you're going to play, right, or how many times you'll pull these arms or display these ads, then just at the beginning we do all of the exploration, and then we just choose, well, so far what's been the best arm, and we always choose that arm. So the index basically is, well, which one maximizes
You also have some kind of recurrent relations on the next steps.
Yes. So so as I said, I'm not going to discuss Giddens' perspective here. Although of course that's classical and very important. I guess in the context of internet ads, these are kind of some of the policies that are the most popular there, which are not, at least not in a direct sense, based on Giddens' index. So I won't discuss that, but we have other kinds of indices, and in this case, our index is just we pick the best arm, and for the remainder of the time, so epsilon times t times, we figure out which is the best arm. Of course, we are likely to make a mistake, but nevertheless, whatever seems to be the best arm at the end of the exploration stage, we just exploit that information for the remainder of the time. So this is called the epsilon first algorithm because, well, at the beginning, for some epsilon kind of proportion of the time, we explore and then we just exploit that information. Now, clearly by the law of large numbers, as t goes to infinity, we have a consistent estimator here. But of course, if t is just some fixed known value, it's not going to infinity, so there's a good chance we might make a mistake, especially if there's if there's several ads that are roughly similar. Okay, so yeah, so again, so now let's consider the case where t is unknown. Now there's kind of a trade-off. So if we don't know what t is, then maybe we assume that t is just kind of going along, and we just want to make sure that we don't make mistakes too often. We want to kind of bound how bad the performance is just over time. So now there becomes a kind of a trade-off. Sometimes we might want to explore, and other times we might want to exploit that information that we have. And so we could try to do something like that epsilon first algorithm, but again, now we don't know what t is, and maybe we just think of t as kind of just increasing, and we want to minimize how bad we do overall. So we could say, well, instead of just at the beginning exploring and then exploiting it, we could start by
he was talking about sensor observation. So if the person dies or your client drops from the network, this kind of rough analogy. So how you take into account the fact that somebody after looking on the advertisement dropped from the game?
The person who's kind of the game for us is as say Yahoo or somebody who's choosing which ads to display.
Okay, well,
so
there's people who are looking on the ads. At some moment they decide, no, that's rubbish is enough, full stop. So it's kind of sensor observations, sensor for guidance. Because if person dies, roughly speaking, that's the fact of life, right? We don't have any more observations. Somehow we update the whole system of indices. If we see that. So this game is not played in your context. Okay, we have statistics that somebody, after looking at your answers, they switch off computer.
So we're looking at every single user as a separate. So what we're thinking is anytime somebody comes to the website, let's say let's for simplicity assume there's only one website we're in charge of, and every time somebody goes to this exact website, we need to display one of these ads for them. So then we display the ad. So somebody comes. We display the ad, and then they either click on it or they don't click on it, and then we see, okay, if they clicked on it, good, we get, we get paid. Otherwise, we get our reward. If they don't click, we don't get paid. So if they just turn off their computer, that's fine because we wait till the next person. It could be them again, could be somebody else. Next person comes to the website, that's kind of a difference with this approach and the more classical approach, where because you can have people dying or leaving, you wind up with kind of a discounting factor, and in this case, there's not going to be a discounting. Okay, so one simple approach, just extending kind of the epsilon first approach. Now, since we don't know how long we'll be playing, how long we'll be showing these ads, we just say, okay, let's start by just doing a step of exploration, right? So that we just get some information. We could maybe explore every single ad once, and then what we do is we can we just say, okay, now a new user comes on the website, and we can, with probability epsilon, we show them a randomly chosen ad. And with probability 1 minus epsilon, we show them what we think is the best ad. So there's still some, so we're optimizing, we're using our information and saying, well, this is what we think is the best ad. But at the same time, we're trying to explore more, and so with some small probability, we gain additional information. Now this can create biases if we use all of our information, right? Because if we choose after we do our first round of exploration, we've kind of said, okay, this is the best arm. We keep pulling it, and so we learn a lot about that arm, and that kind of creates some bias if we use all that information. So for this reason, when we talk about how good every arm is, we only use information from exploration steps and no information from exploitation steps. Otherwise, we wind up with bias. But this is a very kind of direct way. So with probability epsilon, we explore, and with probability 1 minus epsilon, we exploit the information that we have. Now, this is a nice approach, but one problem with it, it's not consistent, because no matter, even as t gets large, no matter how large t is, there's probability epsilon that will just randomly choose an arm. So if we want to get some kind of a consistency, we can assume that epsilon is not just epsilon, but some sequence of epsilons going to 0 in a particular way.
I apologize for the interruption, but maybe it's of interest, because there was also some guy, Thomas Kakava, in Stanford, and he did the following problem. You have a number of coins, and you don't know which is P and Q, right? So you want simultaneously to get maximum amount of money and learn which core is better, which was. So you try, okay? So there's a trade-off that's similar a bit. You try one coin, you have success. You want to try more, but maybe maybe the other is much better. And this is also optimal strategy. Thomas Cover, you know,
Cover and height.
cover and height. Yeah.
Yeah.
So that's a bit similar. It's similar.
Yeah, it sounds like you should be able to formulate it.
It's
in this
similar
kind of
to your
framework.
problem, yes. And so you want to explore all these coins. And simultaneously you want to get the maximum amount of money of this.
Yeah.
Okay.
Yeah, I think that's.
So, more or less equivalent.
Yeah, I think so. Yes. Okay. Yeah. So if we just keep epsilon fixed, that will create. That will mean that we're not consistent because no matter how many times we've displayed ads, the probability we'll show the wrong ad is about epsilon. So what we can do is we could take epsilon going to 0 in some reasonable way. We don't want epsilon going to 0 too fast. But if we take epsilon going to 0, that will mean that we take into account that we keep getting more information. The more information we get, the less we need to explore and the more we can exploit. And so in a paper by Auer et al., 2002, they proved they considered a particular way of choosing epsilon n to go to 0. And maybe I should add this paper of Auer et al., 2002, is probably one of the first to really start applying multi-bandit problems systematically to ad placement. It's not fair really to say it's the first. There's definitely a couple papers from the 1990s that were already doing that. But I think this is the paper that really started people thinking about this. And most papers in ad placement using multi-bandit problems cite this
So how it
paper.
goes along with Thomas Cover, he had exploration periods and exploitation. So if you have very many successes, you don't want to switch. Okay? So you carry on. Then you have a number of failures. Then, if you have number of failures with your particular coin, you go to exploitation, to exploration. So you try other, depending how long are you already in business, you need more and more, if you believe in this coin, then you need more and more failure before you start doubt, is this the best or not the best? It depends how many already trials you have. So it depends, somehow he constructed, it's a very clever construction of my cover.
I guess it's maybe better to just for I have no profound understanding of the problem, but I believe it's better to to build your strategy on at each step. I mean,
Okay, you have memory. You have memory. The longer you use your coin, the more failure you will need to go to drop this coin and go for exploration. So it's all.
Are you talking about a problem where you have, like in his setting,
it's like a great problem again. You have.
Okay, so you're looking for the coin which is the most favorable.
Oh yes. So you have n coins. One of them is more favorable. More favorable. But you don't know anything before you start to talk. It's like here.
It's the same.
It's basically the same. But why is this no mention of cover? How this goes along with Thomas Cover approach? Is it the same basically, or it's different?
I mean, it's a similar idea, except here we're choosing whether to explore or to exploit independent of what we actually observe during the exploitation phase.
I believe that what you're talking about is simply a different algorithm in the same context.
Okay.
Which is the algorithm you're talking about is maybe the one where you actually continue flipping the coin.
Yes.
As long as you're winning. And,
Yes. When you have flipping without success, then you look at your history. How many times I already used it. So if you have very good history in the past, then how many failure I should have with this coin before I believe no, I was wrong. I should try another one.
Yeah. I see.
Yeah.
So maybe just different algorithm.
It's a different algorithm, similar idea. It's also, I guess, it's a different way of trading off between exploration and exploitation. In this algorithm, we just kind of randomly choose to explore to exploit. There, you take into account.
But this is not optimal because this how he proves that he's kind of optimal.
Okay.
It's not clearly not optimal. Because Thomas Kammer he doesn't prove that what he's doing is a kind of the best possible.
But maybe he proved it in the case where the outcomes isn't the fact that the outcome and the problem you're talking about quite simple. Whereas here,
0-1, yes.
Yeah.
For Thomas Kammer, 0-1.
Yeah, I guess here maybe it's maybe.
Well, I mean, the application we're interested in is basically still 0-1, but the same approach could be done even if it's not 0 and 1. But that's very interesting, especially there's some optimality behind that. So
I can't, you know, I can't give you the full guarantee, but I believe that Thomas he's studied also the optimality somehow.
Okay. So that's very interesting. I'm not aware of that, and especially within the kind of the computer science literature on this, I have not seen references to that. So it could be that people in this area just aren't aware of those results. Could be a very useful result. You know, or I mean, it's a different algorithm than this one, and if there's some sense, there might be some ways in which it's a better algorithm. I'll talk about another algorithm after this one which, in some sense, gets to that kind of an idea of seeing how long we've been doing well or not in a different way. So that'll be the next algorithm. But I just want to finish mentioning this sort of epsilon greedy algorithm, where if we take the epsilon to be a sequence, so epsilon is the probability of exploring as opposed to exploiting what we know. And clearly, if we've done enough steps of exploration, then we don't need to explore that much. So if we take epsilon n going to 0 in some reasonable way, then we can get some result. In particular, Auer et al. Show that if you choose epsilon in this way, where c is just some constant greater than 0, k is a constant greater than 1. Now, there is something, this depends on d squared, which is something we actually don't know and are trying to figure out. D squared is the minimum distance between the best arm and the expected reward from any of the suboptimal arms. So the smallest distance. Kind of makes sense that when we have arms, two arms that are, the optimal arm is very close to another arm, it'll need much more time before we can discern the difference. Although at the same time we could say if we make a mistake there, the mistake is not that bad. But still, we'd like to get the best arm, and so epsilon n does depend on d squared. However, since we have c and k that we have a lot of control over, basically, even if we don't know d squared, we can choose some constant divided by n, and we still get some optimality guarantees. Specifically, they guarantee that with this algorithm, we'll choose a suboptimal arm with a probability that decays, well, in this way, roughly like 1 over n. So the probability of choosing the wrong arm will go to 0. Okay. So let me discuss now a different approach, which is maybe a little bit closer in spirit to the Cover-Thomas approach, although it's still quite different. This is called the UCB1 algorithm, sometimes kind of referred to as optimism in the face of uncertainty. And the idea here is we don't divide. I'm sorry. Yeah, this is probably this is a good time for a break. Maybe yes, let's. Okay, so in the previous algorithm, we discussed ways where we kind of separate exploration and exploitation steps from each other, right? If t is known, we just first explore it, then we exploit our information. In epsilon greedy, we kind of every now and again with probability epsilon do an exploration step, and the rest of the time we're exploiting what we know. And then we saw we could take epsilon n going to 0, and that way we kind of get some kind of consistency that eventually we'll figure out what the best arm is and just pull that arm. But a different approach is one where we don't differentiate between exploration and exploitation, kind of smoothly work on both of them. And so this algorithm UCB1. UCB comes from upper confidence bound. And let me describe this. So assume that the distribution of rewards has support contained in some finite set from 0 to b. Again, in the context of ads, we usually think that we either have a click or we don't have a click. So basically, b would be just 1. But the result is true in a little bit more generality. And the way this works is, to begin with, maybe we pull each arm just to get some information. But after that, what we do, so let n sub I be the number of times we've pulled arm I thus far, and let mu hat I be, the estimate of the mean, right? Sometimes we use the notation x bar, but here I'm using mu hat I as estimating the mean. But we add to this a little bit of a kind of a confidence interval. So we could think, well, maybe, right, we know that our estimate is off, right? We know it's not exactly the right value. So we can construct some confidence interval saying, well, maybe it's a little bit higher or a little bit lower. And in this case, we say, let's just consider the upper confidence interval and just kind of give, so we're kind of optimistic and say, let's just give the benefit of the doubt to every arm by looking at the upper bounds of its confidence interval. Confidence interval is not done in the standard way we do statistics, but it's chosen in a particular way, which I'll talk a little bit more about later. So we have this, so for every arm we have mu I plus a little bit. And what we choose when we say let's choose the best arm, we choose not the one with the largest mu I, but the largest kind of upper confidence interval. So the one with the largest, this index here. So here T is how many times we've already been working on this, how many times we've just pulled any arm. And n sub I is specifically how many times we pulled arm I. So what happens is, as time goes on, if there's an arm that we haven't pulled very many times, its upper confidence band starts getting larger, right? We haven't pulled it in a long time, so ni is staying fixed, but t is increasing, and so all of a sudden some arm that before didn't seem to be such a good arm, all of a sudden now we say, hey, you know, maybe it's worthwhile going back to that arm. And so kind of in this way we kind of trade off exploration exploitation in just that if we haven't explored an arm for some long period of time, all of a sudden its upper confidence bound starts getting big, and we go back and kind of explore that and see if maybe actually it's a good arm to use or not. And similarly for the currently best arm, the more times we pull it, the bigger n sub I gets, and so this upper bound gets a bit smaller, right? So that's kind of the idea of how this algorithm works. And just for my notation, let me denote this sample mean. And basically, for the sample mean, it doesn't matter how many times we've done this. It just matters how many times we specifically pulled arm I. So it's basically just a function of how many times we pulled arm I. Whereas for this kind of upper confidence bound, that's both a function of n sub I and of t. Yeah, this should be t, not t minus 1. That's a typo. So that's the notation for this, and I want to, and so we can get. This was also from the paper of Auer et al., and it was kind of fine-tuned a bit in a paper Ozibert et al. That the expected regret. So the regret is, well, it's defined here. The expected reward had to be always pull the best arm, minus the expected reward from following this procedure. And it can be shown that this is big theta b squared log t. So big theta, of course, is like big O. Let me maybe write it down. Big theta is big O, kind of set minus little o. So everything that's actually on this order and not smaller. In the paper they actually give more specific bounds or more specific bounds, and they show. So I'm writing this here for b equals 1, but we can do this for any b, but I'm just writing it down for b equals 1. That's the expected regret is bounded this way. Mu star is the expected reward from the best arm, and here all of the sums are, well, at least this arm, this sum here is over all suboptimal arms. Here, I guess technically it's also over all suboptimal arms, but we could write it for all of them because we have no problem, or it's just going to be reduced to 0 in the case where we have the optimal arm. So this is the bound on the regrets, and I wanted to briefly say a little bit about where this bound comes from. I won't go into very detailed proof because it gets kind of, not necessarily difficult, but very kind of technical in some of the steps. So I'll kind of skip some of the steps and just start with this kind of partial result. So it can be shown that for any suboptimal arm, the number of times that we pull this arm up to time t will be bounded by this, maybe not very intuitive, upper bound. But there is a little bit of intuition I can give here. We're basically saying, so we're summing over SI, and SI are all the times where mu I hat was, or the kind of confidence bound was, well, if we take in kind of the lower confidence bound, it would have been above the true mu I. And SI is, we're kind of assuming those are the times when the optimal arm was within its confidence interval. So we can get this situation, and the reason I didn't feel it's that important to include this step of how we get this bound is that this bound doesn't really depend on the form of our upper confidence interval. So this is just some procedure. We can go with some upper bounding that is basically going to be true no matter what we add to mu I. And so if the idea is, well, we can kind of intuitively see that we'd like to add something to mu I and get this kind of upper confidence bound approach, but why should it be specifically something of this form? And so I don't think that the proof is that illustrative of how, it says that much how we get this upper bound, because it doesn't depend on how we choose CI. But the next step really explains why we need CI to be of the form that it's been chosen to be. So we can see that in order to get some bound on the number of times we use a suboptimal arm, we need to bound these two probabilities. Now, we've assumed that the support of our rewards is on 0, 1, right? Before I had 0b, but then I said, for the proof, let's just consider the case where b equals to 1. And in that case, these are just our sample means, and we want to basically get some reasonable upper bounds for these probabilities. So getting upper bounds for these kind of probabilities where the sum, where these are x bar, or sample means of random variables in 0, 1, that's a very standard problem. And in particular, we can look at the Hefting inequality. There's also a number of variations of this inequality. But basically, the Hefting inequality tells us that when we have sample means of IID random variables with support 0, 1, we can bound these probabilities by this kind of exponential function, e to the minus 2 times n, where n is the number of random variables that we're averaging together, times c squared, where c is exactly this constant, right, which is exactly our upper confidence bound. And so we can apply the Hefting inequality to these situations. And for the first probability, based on the optimal arm, we get that this probability is bounded by e to the minus 0.5 times s, where s is the number of random variables we've been averaging together, times the upper bound c squared. So now let's just see what that amounts to, right? We take this 0.5s c squared, and we plug in our c squared, or our c, which is exactly this value here. The squaring gets rid of the square root. The multiplication by s gets rid of the s. And we're left with 4 times log r, or log r to the power 4. So plugging this into the first equation means that we can upper bound by r to the minus 4, and similarly with the second equation. So basically, the way the constant was chosen was to guarantee that we can upper bound this probability using the Hefting inequality by r to the minus 4. But why do we want to do that? Why did we choose the constant in such a way? Well, if we come back here, we see, right, so we're able to bound these by things that do not depend on s and si. So when we are adding over si and s, that just gives us basically times r and times r squared. And so this upper bound of r to the minus 4 times the r squared gives us r to the minus 2, which is still summable. So that's the motivation for choosing this particular constant. And so we can plug that in again. Right, so for each one we get r to the minus, for each of these probabilities, we get r to the minus 4, so we have 2 of them. So we get this sum, and then we add up the first 2 sums, and that gives us 2 to the r to the minus 2. And that is something we know how to sum, gives us pi squared over 3, because of the multiplication by 2. So that's the intuition for specifically why we chose those C's. And of course we have this kind of integer part plus 1, that can be upper bounded by the term inside plus 1. And for regrets, that's going to be, right, it's exactly, so the regret is what would have happened if we always pressed the optimal arm minus the arm we actually chose times the expected number of times we actually chose the suboptimal arm. And, well, we were able to represent this expectation as above, so that's where we get the formula. So again, I didn't go into all of the details, but I think it showed how we got that, why the form for C. And the one thing I want to comment on here is it kind of shows how we could perhaps generalize this approach, because we see really everything at some point where things really depend on kind of the distributions of our observations is through these 2 inequalities. But we can generalize these kind of inequalities. All right, so when we're between 0 and 1, of course, we can use Hoeffding inequality, and Hoeffding is easily generalized to being between 0 and positive b. But if we have exponential moments, there's ways to choose things, right, to get similar upper bounds, just so long as everything has some kind of exponential moment. And even if we have some kind of dependence between observations, if they satisfy, if they kind of or they have a martingale structure, we can use the Azuma inequality. So there's Azuma inequality. It's
For martingale.
it's basically the same thing, but
Yeah, it's the same flavor.
I know.
yeah, basically Hoeffding inequality for martingales. So we can see that that this approach actually can be generalized in quite a few directions. I haven't written any such kind of statements here, but it is just interesting. This is a fairly general way of approaching this problem, and and allows us to create a lot of different approaches and different algorithms in different situations. And maybe I'll mention, in a paper by Audibert et al., they thought, well, maybe if they also estimate variance, they can get better results. And so they chose a same idea, but now the upper bound, the upper confidence bound, takes into account some estimate of the variance for each arm. And they wind up getting better results in this case. Slightly better. And remember before it was big theta b squared log n, and here they're able to show that it's just b instead of b squared, but add to it the maximum of the sigmas. But but on a bounded domain, the sigmas are going to be less than b, so it is at least some improvement on the growth of the regret in this situation. Okay, so this is basically what I wanted to say about multi-arm bandit problems. I want to discuss a few open problems, and as I mentioned last time, I wasn't able to finish my lecture last time, and I would like to maybe go back and say a little bit more about that in the remaining 40 minutes or so. But let me just briefly discuss some open problems. The first issue is this one that's we've discussed several times before. Really, in reality, there's additional context that we have. The probability, the arms change based on which user comes on which website, and that's not taking accounts here. There's been some work on that. The papers I've seen, I've not. I mean, they have some approaches, but it almost feels like they're kind of estimating for different contexts separately. And when you have a lot of contexts, it's hard to see how you can really interpret that. But I think that's a very, very important problem. Again, one people are working on, but still there's a lot, I think, to be done there. Another one is we have a lot of history. There's lots of ads that have been shown, and sometimes once we have the information, we have the data about which ads have been shown, but we don't know what approaches or what policies were being used. So how can we make use of this this wealth of information in situations where we don't know what policies there were, and so that means there might be all kinds of biases. We may have chosen certain ads a lot more than others. So in the absence of that, what can we say? And again, there's been a number of papers working in this direction. I think that's also a very important problem here. And then lastly, I'll mention how we can do this in that framework that we discussed at the beginning, where we have to get not just one click, but in order to get paid, we need multiple clicks at once. So is there a way to somehow combine multi-arm bandit problems with that stochastic knapsack approach? And I'm not aware of too much work in this kind of direction.
I
yes.
have a question concerning point 2. Can you,
Yeah.
maybe I missed something, but can you explain a bit more what's the problem here?
Okay, so we have data.
Yeah.
We can say, okay, we showed this this ad many times, and we show different ads, and here's how much they've been clicked. But how do we then use that information and then follow some policy of the form that I've discussed, where certain ads we've clicked on, we've shown many times, others fewer times, and we may have just had a very strong bias towards ones, towards certain ads and not other ones, and so that I think creates some. So you can't just use that data directly.
Okay. For instance, here just in the case of the simple, I don't remember the name, the UCD one where you had the epsilon n tending to 0 with n.
Mm-hmm.
Yeah. In this case, epsilon n was depending on the size of the data set n, but was not actually a data tuned with. Was not actually database. This epsilon.
Here, yeah, it's not.
This is what something you would like to do. Find epsilon n depending on the data that you could compute with the data.
For instance, or because you could say we already have observed a lot, so if we want to start with that information, we could say how does that affect how we choose things.
Okay.
Or for
this is not done. Up to you.
I'm aware of 2 papers that work on that. Probably there's more, but I think they don't completely solve the problem. You know, they consider in particular situations certain things that you could do.
Okay, and so is there? Can I ask more questions? Up to your knowledge, is there some algorithms in the case of the multi-arm bandit problem which are known to be universally consistent?
I don't know.
In the sense that for any distribution of for any values of p, PIs, the probability of gain of the machines, then the algorithm is consistent.
So this epsilon greedy algorithm is consistent in the sense that as time goes to infinity, it will definitely, so long as you make epsilon n go to 0 fast enough but not too fast, you will definitely converge to the right arm. That's basically what this proposition is saying, that it is going to be consistent. Yeah. So now that doesn't mean it's the best. In other terms, another way of talking about it is in terms of regret, which is that a lot of time you have chosen the wrong arm. So maybe your regret might be fairly large because at the beginning, before you kind of get to the right arm, you've maybe selected the wrong arm too many times. So if your metric is in terms of regrets, which is something that that's just kind of increasing. So it's not necessarily optimal in this sense, but that's optimal in the sense of consistency. I shouldn't say optimal. There's other algorithms that are consistent as well. Okay. Okay. So. Yeah, so as I said, I wanted to, I guess we need to return this by 9, but I still have maybe a half hour, and I wanted to say a little more about the talk I didn't finish last time. So, yeah, so this is kind of switching gears quite a lot, but unfortunately did not have enough time to finish this last time. I really say anywhere near as much as I wanted to say about it, and since I do have some time, I thought maybe I could talk a little bit more about this. And here, the basic issue is what happens when, I guess in some sense it's a question of robustness. We have certain models that look heavy-tailed in a certain sense, but technically they're light-tailed. And then there's other models that look, in a certain sense, light-tailed, but actually they're heavy-tailed. I did talk quite a bit about part one, although there were still a number of things I wanted to say. But let me maybe, since we don't have too much time, say something about part two, where we have this case where we have a distribution that kind of looks and feels like it's light-tailed, but actually it has heavy tails. So consider just a very simple situation. We have a mixture. So we have a CDF of this form, right? It's a mixture of F1 and F2, where F1 is in the domain of attraction of the normal distribution, and F2 is in the domain of attraction of some infinite variance stable distribution. And we assume that the parameter P is very small. So mostly, right, we feel that our data comes from F1. Right? It looks like F1, it kind of feels like F1, but every now and again we get some we might get some pretty extreme observations because of F2. And such models appear in some applications, for instance, in the dispersal of seeds. So seeds tend to travel very far, or they can travel very far when they're kind of picked up by certain winds. But on the other hand, most seeds don't go very far. Yeah, seeds like from a fruit or a tree, so they can spread that way. And travel patterns of humans. I kind of said the opposite in my previous lecture, saying that people tend to move kind of far, but not too far. I might seem to be contradicting myself, but this is from a different perspective. If I'm just, walking around the city, I might seem to be going really far, and then, I stop and here's my house. On the other hand, if kind of you look at me globally, most of the time I'm in Charlotte and, kind of behaving that way. And then all of a sudden, here I'm in Moscow. So all of a sudden I've traveled a huge distance. It's very rare. I fortunately don't get to come here too often. So usually I'm in Charlotte. Usually I'm governed by F1. But every now and again I take a really huge step. I take a plane in Moscow or somewhere else. So in that kind of sense, this is the kind of travel patterns that Brockman and Hafendahl were studying. And they saw that this kind of a model seems to do a pretty reasonable job. So, what is the effect of, so what happens when we work with this kind of a light-tailed data, but with a heavy-tailed impurity? So what is the effect of this impurity?
Which is the range in terms of P when you are close to Gaussian. So you have N as a function of P. Which is the range when you are close to Gaussian and when you are close to stable. For some moderate, because the technical details not necessarily all should, but that's in terms we have N of P. Up to this end, you are close to Gaussian. After this end, you are close to stable. How the function of P behaves?
Okay.
For small P. That's cross a little better.
Oh, okay. So you want to skip the details and skip to the punchline. I guess it is late and everyone's tired. So this is basically the punchline. I'm slightly considering a more general model. Maybe let me just briefly mention this slight generalization, where F1 belongs to the domain of normal attraction. So that just means the scaling is of the form n to the -1 over alpha. That's what it means, normal domain attraction for the central limit theorem, as opposed to a more general scaling term. So F1 is in the normal domain of attraction of an alpha 1 stable distribution, and F2 is in that of an alpha 2 stable distribution with 0 less than alpha 2 less than alpha 1 less or equal to 2. So this is our framework. And in this case, so We can consider sums of IID random variables from this mixture, and what happens when p goes to 0 and n goes to infinity. Basically what we could say is that when n is smaller than, so one way to, so we can get some limit theorems for this, but one way to interpret these limit theorems is, let's just say, well, what if p is really small, and what happens as n starts getting bigger? So if n is could be small, but much smaller. I mean, could be large, but much smaller than p to the minus 1 over minus alpha 2 over alpha 1.
So if you go, along this line, you change p and then simultaneously. Will it go to converge to mixture or to what? What will be?
Yeah. So it converges to the convolution.
Convolution.
Yeah.
When you simultaneously change n and p, you always on the boundary.
Yeah.
Convolution.
Let me maybe, I won't maybe go into all the technical details, but let me maybe just make sure we get the framework exact of what's going on. Right, so we have this mixture. We consider the mixture distribution, and then we take this is just a representation of the mixture. Okay, so let's consider a sequence of pn's going to 0, and we take a sequence of IID random variables from this mixture with a given pn, and we add them together. Now what happens when n goes to infinity? So n is going to infinity, and pn simultaneously is going to 0. So what happens to this sum? We know what would happen if pn were fixed, since it's, the heavier tails would win, and we'd be in the domain of attraction of the alpha 2 distribution. But since p is going to 0, that will change the situation somewhat. And what we'll see is, in this case, if pn times n to the 1 minus alpha 2 over alpha 1 goes to 0, so alpha 2 over alpha 1, of course, is between 0 and 1, so we have n to the 1 minus alpha 2 over alpha 1 is still going to infinity, but pn is going to 0 fast enough that the whole thing goes to 0. In this case, we can find appropriate constants eta n, for which the kind of central, this summation under this scaling, just by alpha 1, still will converge to alpha 1. So this is the case where pn is kind of going to 0 fast enough, and the really heavy tails from alpha 2 don't really play much of a role, and things behave as if it was just the lighter tail. But on the other hand, if this pn times n to the 1 minus alpha over alpha 2 converges to some constant between 0 and infinity, then the sum, now under slightly different scaling, will converge in distribution to our alpha 1, right? Alpha 1 is just our alpha 1 stable distribution, times this exact term to the minus alpha 2, plus r alpha 2, the kind of heavier tailed one. And kappa kind of tells us how much of the lighter tailed one we still have. So if kappa is infinity, well, we use the standard convention, 1 over infinity is 0, and so the heavy tails win out. Otherwise, the larger kappa is kind of the less of alpha of the lighter tailed one we have, but still it's a little bit there, and so we have this kind of convolution as our limits. Okay, and now one way to think about this is we could think, well, Pn in applications isn't really changing, only n is changing, but if p is some very small constant, then if n is large, but n is still much smaller than p to the minus 1 over 1 minus alpha 2 over alpha 1, kind of comparing with this, this kind of term here, if it's much smaller than this term, it's well approximated by the alpha 1 stable distribution, the sort of the lighter tailed one. But and then if n is kind of on the order of this term, it should be well approximated by some kind of convolution of alpha 1 and alpha 2 stable distributions. But once n gets really big, much bigger than this term, then the heavy tails win out. No matter how small p was, we still had heavy tails, and the heavy tails win out, and we're well approximated by alpha 2 distribution, the heavier tailed one. So for this situation, these are kind of the way we can approximate things. And one thing.
What does it mean, well approximated? Just to live in the limit?
Well, in the limit,
Because well, it's a little bit, should be precise somehow.
well, it's yeah, I don't have.
Maybe very slowly, if it's maybe very slowly.
Well, the convergence may be very, very slow, but in some sense, this term kind of tells us a little bit. So when we're less than or not much bigger than this term, then we really don't expect to get alpha 2 stable. So it's really, n needs to be much larger than this term before we really start reaching the limits. Maybe that's a more precise way of saying it, that n must be much bigger than this term, so we can't just say, well, let's approximate it by alpha 2 stable that we know is converging to, especially if it's not much bigger than this term, then there's no reason to suspect it will be anything like, well, it could be kind of like that kind of convolution we saw, but it's not necessarily, but it shouldn't be it should be quite far from alpha 2. So we need n to be very, very large for this asymptotic approximation to actually start to take hold. So we could kind of see that for some aggregation levels, this might be well approximated by a normal distribution, even though it's actually in the domain of attraction of some heavy. Now let's consider the case alpha 1 is 2, where we have this mixture of light tails and infinite variance, and then we can see that. For some aggregation levels, it could be very well approximated by a normal, even though it's actually converging to an infinite variance stable distribution. And not very happy with how I wrote this last point, but what I think, what I meant to say here is, what I think would be very interesting is to see how robust usual procedures for the normal distribution and inference procedures would be in this case, because it looks like a normal distribution, and we probably would not be able to distinguish it, and really necessarily from if you don't have a very, very large data set, be able to understand that we actually have this heavy-tailed impurity. So we might be very tempted to use normal theory to do statistical analysis, and I think that's an interesting question of what the effect would be.
If you are a practitioner, you will look for sums, but for maximal values, and you will solve it much quicker. No practitioner will take some sums, that doesn't make sense. Because you're losing effects we are looking for by averaging.
Mm-hmm.
So any practical person will look only for maximum values.
So if you're specifically interested in understanding the tails, of course, that's what you would do.
But I take an average. That makes sense.
But if you kind of think, I guess in some sense this is showing how we can arise with something that looks very much like a normal, but actually has really heavy tails, and that I think leads to this question of, if we do have such data which looks normal, but we don't know if it does have this kind of heavy tail impurity, what would be the effect of?
What is the statistics look for the first 200 maximum values and compare?
Sure, there's different procedures, and if we have a rich enough data set, we could definitely, there's lots of ways to do it. We could look at some hill estimator or something else to try and understand the tails. But if we wind up with a situation where we don't have, we might have a large data set, but maybe not large enough to really detect that.
That's right.
Okay. I guess everyone looks seems to be a bit tired, and it's a Thursday, so probably we don't have too much time anyway if we want to return the computer on time. So maybe, well, I'll be happy to take more questions.
Tomorrow.
Tomorrow, I'll be happy to take them now. Tomorrow, at any time.
There's a problem of estimating of B.
We haven't considered estimation.
Could you please give a couple of references?
Oh, yes. So here's the references. So this is, this is the main paper. This is kind of an early version. Unfortunately, the main paper hasn't come out yet. It was accepted by Theory Probability and its applications, but hasn't been published yet. A kind of preliminary version of these results in a very short way is published in Doklady. And this motivation about that I didn't discuss today, but that I discussed last week, coming from computer science, that's been accepted, and we in this paper by my paper with actually that paper is my one paper with my wife, Li-Juan Chao. Very happy to have a paper with her. She's a computer scientist, and so that's in the computer science conference. Applying these kind of models to some computer science things. But yeah, these are the references for this talk, both the part that I was able to discuss last week and also the part that I discussed today.
I see this is your research, but who other? Who are other mathematicians who have been working?
Well, specifically the models that I discussed here.
This is something very special.
I'm not so aware there's in this kind of formulation. There is a paper which has similar kind of ideas about summation of random variables under different kinds of tail truncation, and that's Chakravarty and Samorodnitsky. I think it's 2012, maybe 2013. So that's probably the only other paper that I know which talks about this kind of summations when you simultaneously modify the tails. Okay. Thank you.